So hopefully everybody had a good break. And where we left off, I'll try to kind of recap and kind of pick back up. So we started talking about nonlinear relationships. So everything we did before the exam was linear, right? We'll talk a little bit more about what nonlinear means, just kind of a refresher here in a second. So I put up, it's going to be kind of, we're finishing up nonlinear relationships today. So this week, we might have some time to introduce the idea of interaction terms today. If not, that's what we're going to focus on Thursday, and that'll bleed over into all of next week. So it used to be like most of the material was like week by week. The rest of the semester, sometimes it'll be kind of covering like a week and a half, right? So we did a week of nonlinear before the exam. We'll do a day today. Then interaction terms will be a day this week, and then full week next week. So kind of like a week and a half for each topic, right? So we're kind of still on week 9, so to speak. I put up kind of the next week, which would be what we start this way, right? Week 10, interaction terms, which will bleed over into next week, week 11. So kind of modules will start to look a little bit different. I'll probably kind of rename this to say like week 10 and 11 next week, since it'll bleed over into next week. But most of the files we're going to use are still everything today is what we had in this week 9 nonlinear relationships module, okay? So I'm going to keep using these nonlinear relationship slides, and then we're going to use this do file for nonlinear spring 2025 as well today, okay? Other than that, I also put down here, just so it's kind of at the very bottom, the next kind of sample questions. You can see I have that next quiz ready to go. So that quiz will be due at the end of next week. So that's going to just cover what we went over before spring break, and then what we kind of finish up today, okay? So you'll have a set of practice problems to look at. That'll be a good refresher of what we were talking about nonlinear relationships. It'll have some carryover interaction terms. But you'll have, about a week and a half, really kind of 2 weeks to kind of look through those practice problems and get on and get that quiz done by the end of next Friday, okay? Other than that, you have that problem set, which is also, I think I have set to be due on April 1st. So I'll probably push that off to be kind of due at the end of next week as well, just to kind of give the due dates to be the same, have a little bit more time to work on that. That's also primarily going to be just focusing on nonlinear relationships. So, probably could have went through a lot of this already based off what we did before spring break. So if you've got a pretty good start on that, maybe some of the last few questions will kind of get answered today, or you'll kind of see more examples of today. Okay. So that's where we're at. You got a problem set and a quiz, which will be due at the end of next week. I think other than that, that should be all the housekeeping stuff. Oh, someone asked me, and I just realized I left them in my office. I have all the exams for those of you who weren't here before spring break. If you didn't get your exam back, I have them in my office. So I actually have office hours today. I'm giving an exam in my other classes, so I'll be there from 2 to 3:30. If you want to hop over after class and grab it, you can do that. Otherwise, I'll make sure I bring them to class on Thursday to kind of give you back to you, okay? Any other questions for me before we jump into things? I also had one more thing I wanted to mention. I actually just updated this before class. So that midterm exam score, your grade should change a little bit. I kind of added in those post-exam questionnaire points, right? So I said, if you did that, you'd get the full 4 points. So as long as you got on and got that done, everybody except for 2 people did that. I don't know why they made that choice, but they did. Everyone's kind of score should update a little bit there. Okay. All right. Any questions before we jump into material here? Okay. So we're going to start, things will move kind of quick. The first half of the class, I guess you could argue it moves quick, but really everything's going to be building on itself now. So missing class periods, missing things are going to be really important that you kind of make sure if you do miss, you're keeping up to date with everything. So we left off talking about these non-linear relationships. I think I introduced the idea of logarithmic relationships. So just to kind of review that, to give a general overview, and the slides kind of provide the mathematical reasoning behind why. I'm never going to make you give me the mathematical proof. All I want you to know is that we have 4 different types of models, right? So we got a level model, a level log model, a log level model, and a log. Is this, yeah, of course. I don't understand why people do that. So I need to, that's because I've got this set to mirror my image. So someone change this. Turn off, no, no, no. Yeah, I don't know why someone switches that over. Okay. So we've got these 4 different types of models. Let me get them all on the same screen here. And really what this refers to is what I'm using for my Y variable and what I'm using for my X variable. So the level, this is everything that we've been doing up to this point. This is just our typical kind of linear relationships, right? We said, how do I interpret the coefficient here? It's just a 1 unit change in X causes our predicted Y to change by whatever that coefficient is. Okay. Nothing new there. Now, the one that's also, I think, maybe not quite as tricky is this log-log model. We're going to use the natural log of Y. We're also going to use the natural log of X, right? We said that makes the interpretation of our coefficient. A 1% change in X causes our predicted Y to change by beta 1%, right? So that's a little bit more clear, right? So why did we say we might like these log-log models in economics? What does this sound kind of similar to? Elasticities, right? So if I replace this with price and quantity, I can get a nice price elasticity of demand, right? So the ones that are a little bit more tricky is when we have these level log relationships. So this would be Y as a function of the natural log of X, and then the natural log of Y as a function of simply the level of X, okay? So anytime I take the natural log, we can kind of think about it. It isn't perfect, isn't really technically the most correct way to say it, but it's like we've converted units into percentages. So now the interpretation of beta 1 here is going to be a 1% change in X, right? Will cause my predicted Y to change by what? It won't just be beta 1. Now, notice Y is still in units, right? So I have a percentage change in X is going to cause a unit change in my Y variable. If I'm going from a percentage to a unit or kind of decimal form, what would I do? So how do I convert a percentage into a probability? I would divide by 100. So the kind of change in Y is beta 1 over 100 units. If I'm working the opposite way, right, where I just have the level of X, it's going to be a 1 unit change in X. I didn't change that, right? It's still in levels, right? Is going to cause my predicted Y to change by what? Well, it's going to be beta 1%. But if I'm going from units to a percentage or probability to percent, what would I do? Multiply by 100, right?
So when you say we're going from probabilities or the other way around?
I mean, we're not technically doing that because these X variables are going to be in dollars or be in inches, right? It's just a way to kind of remember that conversion that you need is if I'm going from percentages to units, it's like I'm going from, if I'm going from percentages to units, it's like I'm going from percentages to probabilities. So what would I do? Divide by 100.
But in the case of it being a dummy variable, it would just be.
Yeah, so what is going to be a problem with these level log, log level, log log models? What variables can I not use? So the natural log of 0 is what? I think we went over this. We said that it is undefined, right? So I can't use variables that have zeros. So automatically, what is that going to rule out? Dummy or indicator variables. I can't use the model if, you know, for instance, my Y variable was my Y variable was a dummy variable. I can't use the natural log of that, right? Because the zeros would all get dropped. I can't take the natural log. So we're going to be somewhat limited when we can use these other models if I'm dealing with dummy variables or categorical variables or things that have zeros in there. Okay. Any other questions over anything here? I know I kind of went through this, but just kind of refresh our memory on what we're doing here. Okay. All right, so just to kind of look at some examples, and I don't think we worked through all of these. This was kind of the reason why we have to divide by 100 if we used a kind of level or linear log or level log model. I'm not going to make you reproduce this. We just have to know that when we're doing that, we divide by 100, right? Going from percent to kind of units. Right? So we kind of already talked through this. We can't use categorical variables. Why might we want to use percentages? So this is going to be probably not something I quiz you on or test you on as much, but just the practicality of this. Why would I want to use percentage changes and things? So if I'm thinking about something like income, going from having $30,000 to $40,000 of income might dramatically change the lifestyle I can have, right? I mean, when I start out with going from 0 to 10,000, having nothing to something compared to nothing is a huge, huge change. But that same $10,000 change going from having 100,000 to 110,000, how much is that going to impact maybe my daily life and my consumption? Not as much, right? So what's going to matter is probably not just the unit change there in income. It's probably going to be more likely we care about percentage changes. So things that, it's kind of hard. There's no like hard and fast rule about when we want to use them, but sometimes it might be that the relationship between two variables, it's likely that the percent change in X matters more or the percent change in Y matters more. So I had kind of an example that I was thinking about. We've got a data set we'll kind of look at here in a second. But let's say I wanted to try to predict college GPAs, like the admissions department here, using your high school rank. Okay. So high school rank is going to be kind of a weird one, but right, if it's measured in terms of percentiles, right? So I'm in the 90th percentile, 95th. As I go higher up in ranking, what's likely going to be true about my college GPA? It's going to go up on average, right? Now, if I went from the 50th to the 60th percentile, this is where maybe it's not always like the income example I gave. Looking at the 50th versus the 60th percentile in high school ranking, I'm probably looking at very similar students. But looking at the 90th compared to the 100th, that 100th percentile, I am looking at extremely probably intelligent individuals, right? So that same 10 percentile increase, it's going to matter more depending on kind of what values of high school ranking I look at. So I might care more about the percentage change. So I'm going to use the natural log of high school ranking, which means how would I interpret beta 1 here? So I always start out with a change in my X variable. So it's a 1 percentage change in my high school ranking or percentile ranking is going to change my predicted college GPA by what? Beta 1? No, right? If I'm going from a natural log, a percentage, to just a level or a linear kind of variable, what do I need to do? Divide by 100. So what's probably going to be true about the size of that coefficient? It's going to be relatively large, right? Because I haven't divided it by 100 yet, right? I haven't scaled it to be kind of give me a nice interpretation. So we would not only expect it to be positive, but because we haven't scaled it at all, it's likely it's going to be a relatively large value, right? Now, once we divide it by 100, GPAs are only measured from 0 to 4, right? So, I mean, we might see something like, I don't know, 20. How can I see a change in the GPA of 20? I don't. Remember, I have to scale it by dividing by 100. Oh, it would be a change of 0.2. So we want to make sure that we kind of divide that coefficient by 100 to get our kind of correct interpretation. Now, does this model explain more of the variation that we see in our dependent variable? So if I want to compare this to just my level or my linear model where I'm not taking the natural log, what are some things that I would look at? The R squared, I can compare the R squared. That tells me the proportion of the variation in GPAs I'm explaining. What's another thing I could look at? The p-value on beta 1, right? There's statistical significance. Which one of those, comparing those two models, which one has more statistical significance? Now, most of the time, those two things would line up suggesting the same model. Not a guarantee, especially once I start adding in additional controls, right? So once I start adding in additional controls, it's not always going to be that the R squared and the p-value on that coefficient suggests that the same model is correct, right? So we're looking for, when can we definitely say this model is better? When both of them kind of suggest that it's better, right? But it doesn't always have to be the case. And we'll kind of look at some examples, right? So you guys are already anticipating everything here, right? Maybe you're looking at the slides and answering as we go, but I'm, hopefully you're kind of thinking about this as we go. So let's go to this data file. Oh, test scores. We don't want this. COVID County data, small free throws, GPA, right? So I've got my global path. Hopefully I've updated it correctly. I'm going to go down here. This is one of the files I gave you, which was GPA data original. Let's make sure we can find that. That's kind of in that week 9 kind of category, right? Oh, go away. There we go. So I'm going to open that up. Now, when I have this original data set, it starts out, all I have is GPA and SAT. I don't have these natural log variables. So what I'm going to have to do is create them, right? So I'm going to use the gen command, right? And just the natural log is essentially a formula. It's just I don't have to type it out. It kind of has it stored behind the scenes. So I'm going to create this new variable, which I'm going to call the natural log of rank. If you wanted to, you could call it high school rank or whatever. And I'm just going to take the natural log, this new variable where I've taken the natural log of the original high school ranking. So I then have 2 models, right? I'm going to run them both. One of them, I'm using the linear or level model. Linear and level, those terms are kind of interchangeable. If you look at the book versus my slides versus Google, you'll see kind of them used interchangeably. So I'm going to run both of these regressions. So I've got my level model here, and then I have a level log or linear log model here. So which one better captures this relationship? Well, we said we could look at the R squared. What's happening to that? Looks like it's going up a little bit. So it looks like maybe using the natural log or the percent change in high school ranking is explaining college GPAs a little bit better. So if I'm an admissions department, right now I'm thinking I might want to be using this model, right? Now I can also look at the p-value. Now here I've got a problem because the p-value are both what? 0. So what can I look at instead that tells me which one is more statistically significant? The test statistic. Whichever test statistic is larger, its p-value would be smaller, right? That test statistic is going to be further out into the tail. So even though I can't see it to the 3rd decimal, I know the p-value on this model is going to be a little bit smaller. So this is an example where both of those suggest that I should be using this linear log model. Okay. Do you have a question?
The R squared.
Mm-hmm.
Is there a certain amount that it needs to go up by to say that it's significant?
Up to what we're doing for the sake of this class, we're just looking to see if it increases. You could create an F test where you're doing model comparison. If you start out assuming the linear model is the preferred, and then you could come up with a p-value to say, can I reject the linear model? I won't make you do that. It gets a little bit trickier once we start adding in control variables. So for the sake of what we're doing, we're just thinking about, is that R squared higher? But yeah, you could come up with a test for it that would have its own p-value to be able to say, can I statistically, or at what statistically significant levels can I say that it increased my R squared? Yep. Okay. Any other questions on this? All right. Let me see. I can't remember what I have in the slides here. I think I've got things here. What do I want? Yeah, so I think I didn't put this all in the slides. I just kind of kept it in the do file. So we'll kind of be staying away from the slides a little bit. So it might be good to take notes on some of the things I'm saying because it doesn't show up in the slides. But I've got some comments here, right? So what if instead I think that I should be using the percentage change in college GPA, right? So maybe I want to run, I don't know, compared to that linear or level model, maybe I want to take the natural log of college GPA, but keep using the level of SAT score. Now, the problem is I haven't created that variable, right? So I'm going to need to create the natural log of GPA. So I'm just going to generate this new variable where I just take the natural log of the variable I'm interested in. Okay. I'm then going to run that level and my now log level model. Okay. So before we compare the two, if I'm looking at this log level model, so I've taken the natural log of my y variable, how would I interpret this coefficient? So it's a 1 what change? My x variable is simply in units. I didn't take the natural log. So it would be if my SAT score changes by 1 point. It's not percentage. I didn't take the natural log on it, right? It's still units. I guess I'm assuming everyone knows how the SAT is measured, right? It's just measured in points, but right. So a 1 point increase in my SAT score would cause my predicted y variable to go up by 0.0007. But wait, what do I need to do to that? Why does that seem really, really small? Well, first of all, 1 more point in the SAT isn't the largest increase, but why is it such a small change in my GPA? If I'm going from level to log, right, thinking about it like units to a percentage, I need to take that coefficient and multiply it by 100. So the actual effect is that the SAT score is up by 1, the percentage change in college GPA would be 0.07, right? Move that decimal 2 places. Okay. So, you know, we're just getting more examples of kind of how we make these interpretations and thinking about these different models. If I then wanted to compare this level model or linear model to this log linear, why can I not look at these R squareds and say, oh, well, this R squared's lower, this has to be the better model? What does the R squared tell me? It's the proportion of variation that I can explain of what? My dependent or my y variable. Are my y variables the same here? No. I've transformed one of them by taking the natural log. The natural log isn't like a nice linear shift. It actually like causes a, different higher or lower values will experience a higher or lower change or larger or smaller change. And so I can't, the variation isn't going to be the same between these two. So when I want to compare these models, I can only compare the models that have the same exact dependent variable. Right? So what could I compare this model to? Not my level, not my level log, but I could compare it to oops, I didn't mean to do that. I could compare it to my log model because now I've got the same dependent variable. So here, if I want to use that R squared, well, what did I not do? Oh, I spelled it wrong is what I did. There we go. Oh, I spelled it wrong everywhere. Jesus. Okay, come on. No, that's right, yeah. SAT, natural log, SAT. Did I not create this already? Not found. Am I looking straight through something? Here, did I create this already? Apparently not, sorry. How did I run that other one before? There we go. So I've got these both created now. There we go. So now I've got my kind of log level model and my log model. Because I have the same dependent variable, I can now compare the R squared and say which of these would be better at capturing this relationship. So 0.1285 compared to 0.1239. Well, it's not a lot better, but in fact, that log model is a little bit worse than my log level model. Once again, I can compare the statistical significance as a second way to check this. Both of them look, they have p-values of 0. Which one of them has a higher test statistic? Just barely that log level model. So both of them still would indicate I should be using the log level as opposed to that log model. Right? So I'm still looking at the same two indicators, right? And a lot of times they would suggest I use the same model. It's just once I start throwing in additional controls, they might not always line up. And we'll see some examples of that here later. Okay. Just to get some practice, how would I interpret this coefficient from my log model? So it's going to be a 1% change in my SAT score, that X variable I was taking the natural log of, is going to cause my predicted Y variable to change by 0.74%, right? So 1% increase in my SAT score would predict that the college GPA increases by a little bit less than 1%. So it's not a perfect carryover, right? Every 1% increase in my SAT will not equate to a 1% increase in my college GPA. Why? SAT score probably doesn't capture effort, your GPA does. That would be my explanation, but there's probably other reasonings behind that as well. But we can kind of start to think about kind of how we make these interpretations. Okay. Does this make any sense? Yeah.
So wouldn't be able to compare this R squared to regression between regular college GPA and SAT.
Nope. Because I have to have my dependent variable be the same. Otherwise, now I can compare it in the sense of I can say that the natural log explains more of the variation of an SAT, explains more of the variation in the natural log of GPA than SAT explains in just simply the variation of GPA, but I can't say which of these captures the relationship better because the variation is going to be different between those two models. So just because I can explain 20% in one and 15 in the other, well, the variation that existed in one of them might have been a lot higher than it is in the other. Yep. Any other questions on this? Okay. So one thing that we didn't quite get to, and I kind of jumped the gun a little bit on this, but if I wanted to compare models, something that I'm not sure if we quite did this before break, but I think it's worth doing again. If I instead run this regression, so let's say I am interested in, okay, I've got multiple variables. So I've got this high school ranking and I've got my SAT score, right? If I want to include both of them, and I'm not sure, should I be using the linear terms or the natural log terms? So I'm trying to predict GPA. I'm going to try to do that using my SAT score and my high school rank. I could you don't have to worry about copying this because we're going to do something that's better. I'm just going to set this up to show you. I could do something like this, where I look at, excuse me, the kind of level and level log models. And then here, I can't look at the statistical significance on one coefficient because I'm interested in multiple variables, but I could still compare the R squared, right? So I could kind of run these two and kind of say, okay, should I be using the natural log of my control variables or should I just be using the linear terms? Well, my R squared is a little bit higher using those natural logs. So if I had to say, I probably would prefer the second model, the one where I'm using the natural logs. However, we have a better test for this, right? Which is if I run these all kind of at the same time, I can kind of do a joint significance test for both of these terms, right? So I could say, okay, if I run the model that has the linear and the nonlinear terms, I then run this joint significance test for the linear terms. What I start out assuming is that they have no effect. So what I'm really starting out assuming here, if these linear terms have no effect, what am I assuming? That the relationship is nonlinear. If I can reject that these coefficients are zero, what I'm saying is the relationship is likely not what I assumed. It's not nonlinear. It's likely to be, in fact, just a linear relationship, right? So I can run this regression, use that test command that does our joint significance test of multiple variables. And I can say here, well, look, I mean, it looks like I strongly reject the null here that these coefficients are zero. It looks like this should be estimating this as a linear relationship. Now, the problem with doing this is if I did the same thing, but I did a test on the log terms, oh, geez, I get that I should reject those as well. So that might be the case. Now, just from what we've talked about, and this isn't quite technically correct, although it is a good indicator. If I'm looking at the joint significance test of my linear versus my nonlinear terms, which of these can I reject at higher levels? So once again, the p-value doesn't help me here because it looks like it's the same. Which of these has a higher test statistic? This test, right? So I can reject that the nonlinear terms have zero coefficients at, the test statistic's almost 4 times as high. Not quite, but, right? So if I had to choose, I probably would choose the nonlinear terms here, right? If I had to choose one over the other. Right? Now, estimating this with both of them in at the same time, I'm getting a really weird nonlinear relationship, and the interpretation would become something outside the scope of this class. Because now if SAT score changes, it's going to change this, but it's also going to change this, and then I have to like do the addition, and it gets you know, a little more complicated than what we're going to dive into. But I just wanted to use this to kind of show you can use these joint significance tests that we've talked about in the past to kind of do tests for these nonlinear terms that you have added in. Okay. All right. Any questions on that before we keep moving here? So I think I've got something else that I wanted to kind of look at. We already talked through this. I kind of jumped the gun. I kind of did this already, right? Doing the log linear relationships. We just have to multiply instead of divide by 100. We've already looked at those in Stata, so we jumped the gun. So if I'm thinking instead, I can compare my polynomial specifications. So, well, I don't want to give you too much. So let's just think about this, right? So if I go now back to, I've got these natural log models I know I can use. So let's say I think it's a nonlinear relationship. I estimate this as a linear log relationship. I want to compare that to when I included a squared term. What's the problem going to be if I want to compare those R squareds? So if I'm looking at, and let me make sure, what did the slide say? Was it high school ranking? That doesn't really matter. So let's say I'm getting the dot cam to show up to you. So let's say I'm trying to predict college GPA, and I'm going to use SAT scores. And I think it's nonlinear, so I include a squared term. I then say, well, you know, I think it's nonlinear, but I don't know if it's a quadratic relationship. Possibly, it's going to be these percentage changes that matter. So I've got two different models. Why can I not compare the same why can I not compare the R squared between these two models, even though they have the same dependent variable? What did we say when I have this squared term? What is it essentially like doing? Well, notice I've got beta 1 here. What do I have up here? A second coefficient. So it's almost like I've added a second variable. So if I add additional variables, what has to happen to the R squared? So instead of comparing the R squared, what should I be comparing between log models and these quadratic models? So I call them quadratic, right? It's just different powers. And here's kind of a log model that we're using. Not my R squared, but my adjusted R squared, or which was sometimes kind of just uses R squared bar. That takes into consideration when I was estimating that quadratic relation to the squared model, I was kind of like adding a second variable. Okay. Does that make sense? Kind of what we've talked about before already. Oops. So let's say here. And I think we've already gone into that, so I don't think there's anything I want to write here. Same. Yeah. Now, once again, I guess to be complete, I'm really hammering this home, but why could I not? Hopefully this is easy at this point. Why could I not compare the log linear relationship to the squared model? Because my dependent variable isn't the same, right? So we're kind of limited on some of the comparisons that we can make because I can only compare models that have the same dependent variable, okay? All right, so we kind of talked through these ideas already, kind of comparing these different models. So which dependent variable, I said we can't compare across them, which one should we use? Right? I can't compare a level log to a log level because they have different dependent variables. Well, which one should I be using? Right? So it's not a great answer. There's not a great statistical answer, I should say. A lot of the times it comes down to thinking harder about what the relationship should look like between these two variables, right? And if percent changes matter in one of them, and in which one would it matter more for? Now, there's also going to be an issue, like even if I have something like income, and maybe I think percent changes matter. So let's say I've got a model. I think I've got some data here. So life expectancy and I'm taking the natural log of income, right? What is going to be true about some people's income? What's the lowest income I could have? What happens if I try to take the natural log of 0? So what's going to happen? If I try to run this, it'll create this and it'll just have like a missing, and it'll basically run the regression, but drop all of those observations where income is 0. So if it drops my observations, what's going to happen to kind of my p-value associated with that coefficient? Well, we could go through the kind of process, right? We have this test statistic. We've got a coefficient over our standard error. Within our standard error, all right, we've got an n down here. So if n goes down, standard error goes up, test statistic goes down, p-value would go down. We're less likely to find statistical significance. We're basically dealing with smaller sample sizes if we try estimating these relationships as natural logs, if that variable has some zeros in it.
Don't you mean p-value would go up?
Oh, sorry, yes. And then we would be more less likely to reject the null. Yep, I'm drawing my arrows too quick there. Yeah. So we want to be careful when we're taking the natural log. If we think there might be, what's a good quick way to check that? Summarize the variable, right? See if there's any that equal to 0. Okay. All right. Where are we at on time? Oh, plenty of time here. So what do I have here? We'll get out of the slides and we'll go to this other data set, which is happiness. Right? So that once again should be laying there in that week 9 files. So we'll start out. Now here I'm going to start to add in some additional control variables, right? So maybe I want to know what's the relationship between happiness, hours worked, children, age. So I'm going to run this linear relationship, but I'm now not just looking at one variable, I'm looking at several. I've got control variables in here, okay? So I look, okay, everything's pretty statistically significant, but maybe I think that there's some nonlinear relationships going on. So the first thing I could do is say, well, I'm going to create these 2 variables, which are, I think that maybe having more children, so having a child has increased my happiness. I imagine if I got to 10, that might not be, I mean, I'm sure it is, but I'm sure the amount of happiness that increased my life by would not be the same, right? And so in economics, a lot of times, what do we think about? The more we have of something, what happens to that marginal utility, happiness, goes down. So we likely think there is a nonlinear relationship. So I'm going to create these new variables, which is just children squared and then hours squared, okay? So I'm going to run this regression where I now have hours worked squared. I didn't call it as long of a name, children and age. So I'm just looking at the kind of relationship of hours worked, not children. I could do the exact same thing. In fact, we will just for the sake of looking at it here. Instead of hours worked squared, since I've already got the variable created, I'll also look at children squared, okay? So I've got these 2 squared variables that I'm going to create. The first one I think might be nonlinear is this relationship between happiness and hours worked. So initially, as I work more, I make more money, life is great. I start working 120 hours a week, not as much happiness, right? So as a matter of fact, right, we can think about, okay, we've got this hours worked. It looks like as I increase the number of hours I'm working by 1, it increases my happiness. However, we're measuring happiness here, but it's doing so at a decreasing rate, right? That squared term has a negative coefficient associated with it. So one thing that we had also talked about is finding turning points. So, right, so if I have happiness and I've got hours worked, give it a second. Maybe. See if it'll go back to the desktop. I'll try switching back and forth here. Nope, did I just lose it? Well, maybe we'll be using the whiteboard here soon. What else might be the issue? So it'd be somewhat limited what I can do for you. Well, I'll be sending an email after class. Or it's this chord because it's barely. So that's not gonna help me. Well. Yes, we are gonna use oh. I haven't done this for a while. So. I'm thinking about I've got happiness here. And I've got my hours worked. And I've got my hours worked squared, right? So that was the variable I was creating in Stata. So we'll be a little less Stata today. Maybe we'll bleed over even more into Thursday's class now because of this. But I can kind of give you some of that. Right? So we said that this was positive 0.005 approximately, right? And then this was negative 0.00003. So there's going to be some number of hours worked where if I think about, okay, what's my marginal effect? So the idea of a marginal effect is taking a derivative of this linear regression equation in respect to the thing that's changing hours worked. So if I take a derivative of this, I'm going to be left with beta 1 plus 2 times beta 2 times the number of hours worked here. Okay. So this was positive, this was negative. That's telling me that there's a certain level of hours worked where eventually that marginal effect will become negative, right? What hours of work would that be? All I'm going to do is set that marginal effect equal to 0, right? I then have a little bit of algebra to do, but we said if we do this, we can always find the turning point. So in Stata, this was done, we could use like that display command. And we said, how can I call these coefficients? Gosh, that's terrible. I forget what the exact name was, but it was whatever our hours worked variable was. After I run the regression, underscore B, HW. All right? That kind of called that coefficient that was associated with that hours worked. And then how can I call the second one? Well, that's the reason why we said instead of using like, if you remember, I remember back to before break, we could use double hashtags. So we didn't have to create the variable ourselves. The problem with that was it was then harder to call that coefficient on the squared term. If I create the squared term variable, well, now I can just, I think here, right, it was like SQ, right? Now I can actually reference what that coefficient is. So what I would want to do is kind of solve this marginal effect for hours worked. So I'd be left with what? That turning point of hours worked would be when we have, negative beta 1 over 2 beta 2, right? And then it's just a matter of plugging in our values and figuring out at what hours worked does working an additional hour actually have a negative impact on my happiness, right? Why might we care about this? Well, if I'm an employer, right, I don't want to push people in terms of overtime, things like that. to a point where they start having negative happiness, they might start, I don't know, stealing from the office closet or doing things that aren't as good for the company, right? This kind of sound familiar, hopefully a little bit of what we had talked about. So we can find these turning points, right? I think if we do the same thing for children, which we no longer can do, but you can take me at my word when I run this. Yeah, we've got a positive and a negative coefficient there as well. So there will be some point where a number of children will actually decrease happiness. I don't know what it is. We could work through the numbers. I'm looking at it here. So 0.03 over 0.008. So what? 5-ish kids, you start to have a decrease in your happiness according to the data, not according to in my opinion or anything like that, right? And this is once again, the powerful is not only am I saying that this is the effect, it's holding constant all those other control variables that we included. So here holding constant age, and then if we're looking at hours worked, holding constant children. If we're looking at the relationship of children, holding constant hours worked. Okay. What else do I want to say here? So, just for the sake of this, let's see if I can. It's still not working. I would really love to show this to you. Otherwise, I might just be hooking up my laptop for future classes. So what else can we do here where I don't have to show you anything on this screen, but still have it be beneficial? So there's one thing that I really wanted to get through, but if I can't even use the dot cam, I can't use the, yeah.
I don't know if you can, but I think what I actually have this projector itself turned off.
Oh, really?
Yeah.
Thank you. So how can I turn the projector off? Let's see. I don't have a remote. Let me try this. This comes back on, it works. And thank you. Well, this might work. Let's see. So there's one thing in the quiz that we haven't talked about yet, which is if I have two models, and I think that when I've got added controls, so let's say I've got model 1 and model 2. Okay? Model 1 is where I want to look at this relationship between happiness and hours worked, and we'll make sure this lines up with what I have in the state of all right. So I've got my happiness, and that's some function of hours worked, and a bunch of other controls. Okay? So I think it was children and age here. For my second model, I've got happiness, but maybe I think I should be estimating using the natural log of hours worked, but I still have all the same controls. Okay? So before, when we were kind of making these comparisons, I was just looking at, cool, hopefully this will work. Thank you for saying something. I need to check that. So I've got these two models. Before we were making comparisons, we didn't have any additional control variables. Well, now I do, right? So I can't just simply look at the R squared because those controls might have a different relationship with the linear term of the variable than they do with the natural log. So what could occur? Well, it could be like screw up kind of like coefficients. There could be like omitted variable bias. It's just weird because it wasn't a completely omitted variable. It was just the wrong, it was the omitted functional form of the variable, which is weird to think about. So what I can actually do is use my regression results from both of these models to determine whether or not I should be using, with all these additional controls, the linear or natural log term of hours worth of variable I'm interested in. So let's see if this now will allow us to kind of look at it. There we go. All right. So we're back on track. So this is just shows you have to be somewhat adaptable. I'm not the most adaptable person, so I'm not the one to take lessons from, but. Okay, so instead of, I kind of have this same idea, right? So the actual name of what we're going to do is called the David McKinnon test. Yes, forget the exact name. So if I run this regression first, this is just our typical linear model. I'm then going to use this predict command. So I think we used this a long time ago. So just to kind of refresh, when I use this predict command, it's going to predict my Y variable using all of the X variables in that regression. So it's going to take the coefficients, multiply them by the actual values for every observation, the actual X values, and come up with a predicted value from this first model. So if I do that all the way over here, I've got my predicted Y value from model 1. Okay. I'm then going to run the same regression, same controls, but I'm going to use the natural log of hours worked, right? So that was that kind of model 2 that you guys can't see over here that I had written up, all right? That's my second model. I'm then going to save those as the predicted Y values from model 2, okay? So I've got my predictions from both of these models. What I'm going to do is run that first model. It looks exactly the same here, but I'm going to include the predictions from model 2. Okay. So to kind of give you a more general term of what we're doing here. So I'll write this out, not even in the context of our example. So let's say I had something like this, and I've got a bunch of additional controls, right? I'm then going to run a second model where I'm using the natural log of one of those variables, but then all of my other controls are exactly the same. I'm then going to come up with my predicted Y values from model 2, from this second model where I was using the natural log. I'm then going to run this original regression again. But I'm going to now include, and we don't know what number it'll be, depends on how many we have, the predictions that I made using the second model that included the natural log of the variable. So this is just a different way of saying, okay, controlling for all of these other variables, instead of just being a linear relationship, if I find statistical significance on the predictions that I made using the natural log, that's telling me that these predictions are going to be better or have some correlation with the actual Y values. So that's going to tell me that this second model was actually coming up with predictions that were explaining more about Y than everything I've included, not everything I've included here, but we're adding some amount of explanation to the values for Y in addition to whatever I had included here. So essentially, by creating the second model's predictions, if we can reject the null for the coefficient on those predictions, that's really telling us that that second model was giving me better ideas of the actual Y values, and that's the model I should be using. So in this case, if I can find statistical significance on model 2's predictions, that's indicating to me I should be using the natural log. Right? So let's look at this in the context of our example. So that's basically what we did. We started out, I kind of did it from both, which I'll kind of break down in a second, but if I run this regression where I've got my linear model, but I now include the predictions that came from my linear log model. So I'm going to do that. Oh, I must not have run this code. There we go. Oh, I didn't like this. Why not? Because I was writing this all out and we didn't actually create this. Hold on. So we left off here. So I've got to create the natural log of all these different variables, hours worked, age, happiness, if I want to use them. So we're going to come down here. So I'm now going to run both of these models, save their predictions. Of course, I already defined it. We're just going to start all the way over, open this up. Okay, we'll come down here, generate my squared variables. We're going to generate the log variables. We're going to come down here, run our regressions, save our predictions. There we go. Now we're going to run our regression of the linear model, but include the predictions from that linear log model. Okay. So when we do that, if we look at that coefficient on my model 2 predictions that came from using the natural log of hours worked, can I say that model 2's predictions are statistically significant? Not even close. So what that's going to indicate to me is I should not be using that model. Well, what was that model? It was using the natural log of hours worked. Okay. So this is going to be an indicator that I shouldn't be using the natural log to pick up this relationship between hours worked and happiness here. Yeah.
You apply the same concept to quadratic models.
So you could, it won't be any different than including the squared term in your original regression. Yeah, because you've got the linear term in bold. Do you know what I'm saying? Like if you compare the linear to your one where you include the, it's not like you're only including the square term, you're including the linear and the square term. So yeah. This is a typo, so we'll just change this. You can also do the opposite, right? So maybe I run the level log model, but I use the predictions from my level model. Now, what should this indicate? So we already know that second model, we couldn't reject the null. So if instead I start out with that second model, but I include my first model, the level model's predictions, what is likely then to be true about the coefficient on my model 1 predictions? Well, if model 2 was not statistically significant, that would indicate I should be using model 1. So when I run model 2, but I include the predictions from model 1, my model 1 predictions should have some statistical significance. So if I go ahead and run this, sure enough, right, not at every single level, but those predictions are statistically significant at the 90–95% level. This would be an indicator that I should be using model 1, which what was model 1? Simply using the linear term. Okay. I could do this technically, not just for a dependent variable that's linear. I could also use a very similar approach if I had a dependent variable that was the natural log, right? So I could run a log model and a log level or log linear model, save the predictions, run both of the models with the other model's predictions and see, can I reject that? In fact, we've got a little bit of time. Let me see if I had this down here. I think there's other things I want to say. I'll kind of go here. So yeah, here we go. Save myself some space here. So I'm going to just copy and paste to make this easier on myself. So I'm going to do another Davidson-McKinnon test. Okay. We're going to come up with instead the natural log. What did I call this? I take the natural log happy. There we go. And then natural log of happiness. So now I'm going to estimate this log linear and this log relationship. Okay. So here's my log linear relationship. I'm going to save the predictions from that model. Here's my log model, save the predictions from that model. So I'm going to go ahead and run these. Okay, I've got an error. All right, why? Because when I use this predict command, what is it doing? It's creating new variables. So I can't create a variable with the same name. So I either have to drop the old predictions or I have to call this something else, right? So I'm going to just drop them just so I don't get confused with like model 1A and model 1B or anything like that. I don't need those values anymore, right? Those are my old models. My new models are the ones where I'm looking at log and log linear, right? Okay, so there we go. Now notice when I'm running these regressions, I don't believe before there wasn't anything after these linear log or linear relationships. Notice when I run these regressions, what is it telling me? Oh, I'm getting missing values. Why am I getting missing values now when I'm running this with a dependent variable that's a log? What must be true about that happiness variable? There must be some zeros in it, right? Sure enough, if I go here, this is also kind of a nice, easy way to kind of cheat. I can sort the data. Oh, happiness, some of these are just missing values, right? So I can't take the natural log of that, okay? So it'll kind of let me know if it drops any values there. That might be some, good indicator like, oh, maybe I should be careful using the natural log of this variable. Ignoring that effect or that factor for a second, I can then look back, okay, I've got my predictions. I'm going to run my log level or my log linear relationship. But I'm going to include the predictions from my second model, which were the log-log model. So when I run this regression, the coefficient on my second model is essentially, do the predictions from that log-log model provide any additional amount of explanation from my y variable that my linear term, right, from this regression doesn't explain? So from that second model, can I say that it has any statistical significance? Not even close, right? So this would indicate I should not be using model 2. Right? So once again, if I do the exact same thing, but instead I look at the log-log relationship, but I include the predictions from my log linear, what should likely be true about the statistical significance on the predictions from model 1? If the predictions on model 2 weren't statistically significant, model 1's predictions should be, right? So we'll go ahead and kind of run this. So this is going to be a good example of, well, look, this is statistically significant at the 90% level. But when I use this type of a test, it's not always going to be conclusive. I've tried to find data sets where it's not. It often is conclusive. There will be times where this p-value starts to get a little bit above 0.1. In which case, which model can we say is better? I mean, we can take the one that has the lower p-value, but none of them would meet kind of our thresholds for statistical significance. So notice, let's just assume that this was, I don't know, 0.11, and you're like, oh, we can't reject the null for either model. Well, yeah, but 0.11 would be a lot better than 0.75, right? So even though it might not always be conclusive at our 90, 95, 99% levels, it will be conclusive in that one of them will be indicated, have an indicator towards its p-value is significantly smaller, right? Even if it fell just on the other side of that threshold. Does that make sense with what I'm saying? I like to say things, but I always get worried when I'm not writing things down at the same time. So just because we don't have a p-value that meets our kind of conventional levels, if this was 0.11, we would still say that, well, we can reject model 1 at much higher levels than we could reject for model 2, indicating we prefer the model 1. What was model 1? That was where we were using that log level relationship. Right? So we can run this David-McKinnon test for the dependent variable being just in its typical units, or we can do it when the dependent variable we've taken the natural log. Any questions on anything here? I know we kind of got derailed a little bit, kind of going back and forth. There's some additional stuff in here, just like more interpretation using this happiness kind of data set. I really wanted to make sure that we had time to get to this because this might be something that you see pop up in those practice exams or kind of on the last kind of question on that problem set. That should really be everything we need. We can kind of go down here and do different types of tests. So here I did it for children as opposed to hours worked. So just different examples. So sometimes I'll throw in additional things here that we don't cover in class. If you are interested, you can kind of work through. It's just more examples of this David-McKinnon test. It's instead of happiness and hours worked, it's for happiness in the relationship with children. But that should be kind of finishing it out, everything that I wanted to kind of get through for nonlinear relationships. I was hoping to have a little bit of time for interaction terms today, but that's okay. We can kind of start those on Thursday and then kind of finish those up next week as well. So before I end today's class, are there any questions or anything? Once again, I know we bounced back and forth, so if something wasn't clear at any point, please ask a clarifying question right now. Right. So I would get pretty comfortable making interpretations from these different log level, linear log, level log models that we've talked about. Also, the stuff we talked about before spring break, a lot more with like our squared terms, our cube terms even that we can add in, thinking about the impacts that these have on our squared. Now, one thing I'll also end with that I know is in the last slide that we said was violated with the squared models. But if I have two variables, and I think I have kind of this logarithmic relationship, right? What assumption is going to be violated? So let's say my data looks something like this, that the relationship actually should be estimated as kind of the natural log of X here. If I try to force this to be linear, what am I doing to my coefficient? I'm forcing it to be, look something like that. So at various points, my errors, and like I drew this, maybe my line of best fit's a little bit higher, but there could be points where all of my errors are actually negative. Sorry, all my errors are positive. I'm predicting values that are too low if I use the linear model. So here, what do we need in order for our line of best fit to be minimized in the sum of our squared error terms? The expected value of our error term at any value of X should be 0. So if we have a nonlinear relationship and we force it to instead be linear, the expected values of our errors here, well, it's not 0. They're all positive. It's going to be some positive value, right? If we allow this to be nonlinear, we'll notice at any X value, I tried to draw this, I've got error, positive and negative errors at any X value. So on average, my errors using the nonlinear relationship are right around 0, right? I've got equal number of errors that are positive as are negative at every X value, which means that if I allow this to be nonlinear, the expected value of my error term at different X values can now be 0. Okay? But if I force it to be linear, that might not be the case. Okay. In which case, that was one of the assumptions we needed to kind of have our coefficients actually be valid. Okay. Any other questions before we get out of here today? So that problem set and that quiz are just related to nonlinear relationship stuff. So we'll obviously kind of progress to the next topic, next class. If you haven't started working on that problem set, I would start doing so soon. Just do it at the end of next week. But the further we get removed from the material, the less likely you are to remember kind of what we went through, especially since we had spring break in the middle, right? Other than that, I will bring those exams next class. I apologize if someone reached out to me. I meant to bring them today. I completely slipped my mind. They're sitting right next to my desk. If you do really want it today, I'm heading back to my office right now. You can come with me. Otherwise, any questions? Well, it stopped raining, so go out, enjoy the rest of the day, and I will see you guys on Thursday. Yeah. I was going to use one, but I'll wait and use it on Thursday. Yep. It's okay. I'll just kick out everything. Yeah. Yep. No worries. Yeah.
One or two things on canvas, which I wasn't exactly sure, but I just thought I just I have this like thing missing, and I don't know if it's counted to my grade. I'm assuming it's probably not because I finished the original one. And right here it says like missing quite a few points in the weighted assignments, but I'm not sure what
Those aren't being factored into the grade.
Okay.
So
Cool.
let me double check. It shouldn't be showing to you any points, or it should be only showing. I guess if you the safer way is to look at the syllabus to see which categories count. Although it should be showing you that those are counting towards your grades. If you go to got your midterm exam, got any class for US,
Did you say that you looked at?
Could be up there. Hold on, let me see what's going on here.
Um,
I moved things around. I might have accidentally, maybe something got.
yeah. Oh, good.
No, I'm glad you said something, because it shouldn't show you anything on the unweighted.
I hate to add on to it, but quiz 4, which is due next week, it
Mhm.
says it's already graded, and I got it.
It should be. I'll check it out.
Yeah,
Because I thought we were gonna get further than we did, so it's got it uploaded to zeros, but I'll get it changed. Also, this in-class quiz, I'll get each when I get back to class. I thought we had time for today, and then we got sidetracked. So yeah, so you've got 9, so it should be 0% of your grade. So why is it showing you?
Thank you.
Yeah, so why is it showing you anything? Because I've got it set to be 0. All the midterm components would be set to be 0, and it's not showing up to 0 for you. Scroll up. You can just keep following. Oh, so it shows you what categories are being weighted by what.
yeah, it says.
So it's calculating it only based off of its static.
Okay.
So it shows you everything just because I don't know why Canvas does it that way. It's something about keeping like all those scores separately.
Okay.
But if it's in any of these categories,
Uh-huh.
it's all 0%.
Okay.
So you would only be looking at kind of what your grade is in each one of these categories and then weighting it by whatever that percent
Okay.
is for that category. Does that make sense?
Yeah.
And I'll get up an Excel file to make it a little bit easier. I'll bring it in Thursday and kind of show you.
Mhm.
You can start to play around with like hypothetical final exam score grades.
Yeah.
And it'll be a little bit easier because you can I'll build in what the percentages are. You'll just plug in what your grades are in these categories and Excel will kind of spit out you like hypothetical grades.
Okay.
But yeah, the only thing that's being counted are going to be these categories right there.
Okay. Perfect.
Okay?
Yeah.
Does that make sense? Yeah, and I'll play around with it because I thought there's a way that, I thought it's supposed to, when I change it, show up to you. There should be something at the bottom where it only shows you the ones that are weighted, but it's definitely putting points next to the ones that are 0%. It shouldn't be doing that. So I'll play around with the view on it and see if I can go into student view and make sure that it's not, try to get that switched. So thank you for saying something. Yes.
Thanks so much. Appreciate it.
You're alive?
Don't worry. Yeah, I'm gonna move it to Thursday and kind of change something. Yeah. Yeah, don't worry about the in-class quiz. I can't unpublish it until I get back to my office. I can, but I'm gonna need to like copy it and do some stuff to say. Don't worry about it. Yeah.
I'm always here. Okay.